Good afternoon. Some would put forth that the internet is a place for freedom of ideas and information. But fellow citizens, let me ask you, are you really free when a webmaster controls what you can and cannot do on a website? Are you really free when Bank of America controls how you interact with your finances and Mark Zuckerberg controls how you view your friends? Now let's be clear, this is not just a conflict of ideology. This is more than a Silicon Valley ideology. We're just 3 hours outside of Silicon Valley, through Sacramento, along Interstate 80, lies another valley, the town of Grass Valley, California, an American town. In Grass Valley, a tweet is still something that comes from birds. I visited Grass Valley a month ago. There I met a man named Joe. He sold plums. Joe the plum guy. And I asked him, Joe, how has the recession hit you? Are you making or losing money? And Joe did not know the answer. He went to his banking website at his local credit union, and it looked like this. It was too difficult for Joe to look at this and know if he was making or losing money. I asked Joe, is this important to you? And he said, well, yes. Now, if only his website looks something like this. Now, sometimes we researchers assume that good ideas will trickle down to practice, but we have known how to make graphs. We have built tools like VisiCalc and Quicken. Yet these ideas did not trickle down to the place most important for Joe, his personal bank account. Why not? Why do some websites present addresses without implementing a map? Why do some websites have page reloads without Ajax? Why do some web merchants lack comparison shopping? Why do some photo sites lack a slideshow? Why has trickle-down ideanomics failed across the internet? There are around 2 million programmers on Earth who are paid to program. There are 175 million websites. There are 1.4 billion internet end users. There are far more websites than there are programmers. And there are even more web users with different goals and tasks to support. And webmasters cannot afford to support all end user goals on all websites. Perhaps, instead of the original webmasters, third-party programmers should enhance sites with mashups, browser extensions, and web proxies. And we now have some great tools to help third parties do these. Tools like Chickenfoot, CoScriptor, Demons, Marmite, Yahoo Pipes, and Highlight. Though these tools make it far easier to change and enhance a particular site, we still have no enhancements for the bulk of the web, like Joe's credit union. And as long as we continue to operate website by website, we will not be able to reform the entire internet. Doing so, website by website, would require every programmer on Earth to enhance multiple websites each, and apply multiple enhancements to them to support multiple users. This is not feasible. We must allow a programmer to enhance multiple sites at once. And in Grass Valley, I learned that real change starts with the grassroots of society. And change for the internet will start with the internet end users. I propose a 3-step program to reform the internet. First, a programmer offers a general enhancement, but they do not tie it to any particular site. Second, we enable internet users to attach the enhancement to any site that they use with a new machine learning by example system. Third, the website pattern will be saved to a central repository so that future users can take advantage of the enhancement without having to do the work themselves. People, this is web reform that scales, and it starts with you. We implemented this as a software prototype called Reform. I'll now give you a short demonstration. Imagine this is your bank account. And it's hard for you to find how you're spending money overall. But you notice down at the bottom, there is a timeline button. And this button calls up a timeline. This timeline knows nothing about this particular website. All it knows is that it needs a time and amount from a website. And it tells Reform, please give me a time and amount from this website. Reform pops up a little menu that you see following the mouse cursor around the screen. And it lets the user specify whenever it finds a time or an amount. So the user moves his mouse cursor over to the date and says, hey, this is the time, and clicks on it. As soon as the user clicks on it, notice that Reform analyzes the page and notices other times that look like the time the user clicked, and also starts drawing a timeline. It feeds back the information that it just extracted to the timeline. Now the user goes to the right and clicks on the balance and says, this is an amount, and this is going to go on the y-axis. And the system graphs the result, and the user gets immediate feedback about what's going on. And you see right in the middle here, this is where the user got paid. And sort of sitting money slowly over time. Looks like he just bought some conference registration. Must be Plum Conference. And the user can now scroll down to the bottom of the page, and scroll back up and check and make sure that it got all the patterns right. So, summary. With just a few clicks, the user is able to apply a new timeline to a new site. By making attachments easy to attach like this, we are dismantling the internet's iron curtain and freeing ourselves from closed business interests. Because, fellow researchers, this curtain was not formed by a conflict of ideology. Nay, this is only a limitation in our current technologies. Let us move forward. This is a map, or this is a website containing nuclear sites in the United States. And you may look at this and wonder, are there many nuclear sites around me that would explode and kill me? Well, it's kind of hard to figure out, isn't it? But we have a map. You go down to the bottom of the screen and click on the map button. This pulls up a map. Just like previously, it does not know anything about this web page yet, but it knows that it needs an address. And it can also take a little details thing. The user clicks on this address, and it immediately starts plotting things. And it got half of them right. And now he clicks on another address, provides another example, and it gets the rest. And you see that living on the East Coast is really dangerous. So it's hard to view websites on a mobile phone. You probably can't read this. So we also built an enhancement that lets the user specify where titles and summaries of articles are. And it takes that information and fills an iPhone template with it. So now you can have a mobile version of any website that has titles and summaries. We also built an enhancement that provides an AJAX feature. So you tell it where the next link of a page is, and now it turns that page into an infinitely scrolling, automatically fetching the next page as it goes. So you can just scroll to the bottom forever, and it puts little headers inside. So let's take a look at what we're doing here. So this is the architecture of traditional enhancements. You tie an enhancement directly to a website. Okay? And this has, so the key thing here is that in order to do this, you have to either write a web scraper, which is going to involve probably regular expressions, or XPaths and DOM patterns. You have to look at the page, see how it's represented, and get in there. Or you're going to be programming to an API. And this is three problems. The first is it's really hard. This turns out to be the hardest thing about building a mashup. The second thing is that it's really brittle. If the website changes, you have to go and hack some code in order to update your enhancement. And the third problem is that it's only tied to one single website. Okay, this is not going to scale to the internet. So Reform breaks this Reform sits in the middle, and it has its own web scraper. It's a special web scraper. This is a web scraper that an end user can use. And provided examples, it can tie any enhancement to any website, and it can tie it to multiple websites, even ones that the original developer did not anticipate. So the key part here is building this web scraper. There are a lot of web scrapers out there. They're very difficult to build, and there's a lot about them. So I'm sort of simplifying them to say that there's sort of fall into two classes. You have the kind that you find in databases conferences in the upper left. These tend to require a lot of user expertise. They have to understand the DOM or the HTML of the actual page and program it. But on the other hand, they work on a whole lot of pages because you can make them work wherever you want. On the other hand, you have things which you might see at Kayur list oftentimes, which are easier to use, but they oftentimes make assumptions about the underlying page, and they only work on some pages. So existing scrapers tend to be up here, and we're, of course we want to be down in the bottom left. We're not there yet, but I'll show you how close we're getting. And here's a little bit, just to give you an idea of how Reform works under the hood. So the user clicks on this time, or this date, and says, hey, this is the time. On the right, I have a visualization of the tree that represents a web page. Every web page is represented with a tree called the document object model. So when the user clicks on this time, it provides Reform with a positive example, and now knows, okay, I can mark this node as a time. And you can see it both on the page and in the DOM. Reform now processes, does some machine learning pattern matching, and says, oh, this other thing looks like that time too, so I'm going to make that a time. And now I'm going to show you something a little bit more than you saw in the previous demo, because if you look over here, this bank actually posts the transaction dates down in a comment. This is the actual transaction, 9/5. And up in the upper left, it posts, this is the date that the bank cares about it for some reason. But we care about the date I actually bought this registration. So we want to try to train Reform to use this. But at the same time, not all transactions have a little thing in the comment. So to do this, we're going to use negative and positive examples. First we go down to the comment field, and we mark this as a time. Now Reform is getting closer, but now it thinks that there's a time up here and a time down here. So we go up to this one, and an X appears, and you click on the X, it labels that as a negative example. And now it remembers, okay, this one's a negative example, and I have a positive example down here, we just need to get this one back. So we go to it, and label it as a time. Okay, now Reform has learned a pattern for the entire page. Something I didn't show you, I only showed you this part of the page earlier, but there's really all this, and every time you click on something, it re-highlights everything else on the page. So the way that we do this learning, we compute a bunch of features for every node. Features like the width of this node is 50 pixels. We also look around the node. We say that, okay, the parent of this node has a width of 80 pixels. And the parent's first child has a text balance in it. Maybe the parent's first child is a number. And a whole bunch of features like this. We compute hundreds of these features for every node. And then we take these and we put them through a support vector machine. And the support vector machine, for every example, it adaptively weights all of these features to choose ones that are most important and explain the examples that we're given. And this in particular contrasts with the way that XPath matching is often done today, where you can specify one type of path that should match all of the nodes that you need. We have hundreds and hundreds of paths, and our support vector machine can choose amongst them. And this way you can tackle the kinds of inconsistent pages like I just showed you. So now that we've labeled all of these nodes, what we've actually labeled is the amount that the node looks like. It's a variable between 0 and 1. It's not just 0 and 1. It's not binary. So you see here the opacity of the yellow represents how much each node looks like a time after we've labeled a time. Okay, and this is over the entire web page. We do the same thing with amount. So these are all the nodes, and these ones tend to be matching stronger as amounts. And we put them together, and this is what it might look like. Our goal is to find a way to pair these times and amounts together now, because we have to graph them as pairs. So not only do we have to figure out what looks like a time, what looks like an amount, we have to put them all together and figure out the relationship between them. So the way we do this is we have this optimization routine that tries to draw horizontal strips across the page. And this assumes that all your data is laid out vertically. So I'll talk a little about the assumptions we do make. So we assume all data is laid out vertically right now. This works on pages like this. We We also have some pages that are laid out horizontally. We don't do this, but it would be really easy to, and we talk about it in the paper. Similarly, there are pages in which data is laid out in grids. We don't handle this, but we could. Some are a little bit more complicated kinds of grids, a little bit not as uniform. These are a little bit more trickier. And then you have some really tricky things where you have nested data. So here we have affiliate faculty, then we have postdoctoral researchers. Within this, we have a bunch of people, and then each person has a list of their affiliations. And figuring out the association, the relationship between all these things is a bit challenging. Another thing that we do not handle, we assume that the page has the data broken up as nodes. If it's just one big piece of text that isn't parsed at all, we can't handle it. But we could handle it in the future if we added in a text parser. So, okay, so that's the basis of how our scraper works. We want to evaluate this in two ways. First thing we did was we want to figure out where these assumptions held and where they broke, and what was how big of an impact they are, and where we stand right now as we're trying to develop reform in the future. So we evaluated the timeline on websites from the internet, and we wanted to test it on pages that could conceivably have timeline data on them. We didn't want to say fail because somebody gave us like a blank web page or a 404 not found page. So we had Mechanical Turk gather 30 web pages. We posted tasks. We said, find pages that you might put a timeline on. And these are unbiased because people did not know how our system worked. And then we classified the failures. Overall, we had a 67% success rate, even with the assumptions that we make so far. So I'll take you through this pie chart now. This is a success, it's the green.
That not only are we able to change websites, but that we actually go to websites that have changes on them. There are a lot of websites out there, and it's impossible for all the programmers to do this. And then secondly, in order to make that work, we need a web scraper that end users can use that can attach enhancements to any site. We need that to be easy and really important, and we provide something like that. So I just want to take a bit to thank my collaborators here. Stephen Drucker from Microsoft Live Labs, Mira Doncheva from Adobe, Ali Rahimi of Intel Research Berkeley, Blake Thompson, an undergrad at University of Washington, and James Lanning, my advisor at the University of Washington. So I just want you to think now, like, what if we could make this work? What if, say, your webmail system could automatically complete email addresses from Facebook? Okay, maybe not just your one webmail system, but what if all of your webmail systems could use the same autocomplete mechanism that somebody wrote? And what if they could automatically complete your email addresses not just from Facebook, but from maybe Google Address Book, or from actual emails that they just scrape addresses from? We are on the road. Shh, don't look. Oh, yeah. Many of you have gathered here today to present new visualizations that transform torrents of data into rich meaning, understanding, and informed action, and new interaction techniques that make web computing more rich, expressive, and humane. These ideas could change people's lives. Yet I hear my colleagues mumble, oh, but how many research ideas actually make it to practice? And isn't the problem here that Microsoft doesn't care or won't implement this feature in the first place? Well, I say to you, fellow researchers, if this starship does not let us affect its course, then let us build a new one with better controls. And let's pilot it to a better world. Because this is the internet dream. This is the internet dream. And it is powered by ideas and information. This is the internet dream. And this dream is steered not by monopolies, but by people who say the words, "I have something to add." This is the internet dream. And to change the form of the internet, we must first understand the form of web pages. That is the reform agenda. Thank you, and God bless humanity. Let's have some citizen action.